Welcome to Lucid Mind Chemistry channel. In this video, I'll be solving Chemistry A-Levels Structured Questions, Paper 41 from October-November 2021. For question timestamps and other useful information, please visit video description. Question 1. When dilute sulfuric acid is electrolyzed, water is split into hydrogen and oxygen. This is the balanced chemical equation. A current of X amperes is passed through the solution for 14 minutes. 462 cm³ of hydrogen are produced at the cathode, measured under room conditions. A. Calculate the number of hydrogen molecules produced during the electrolysis. The formula for molecules is number of molecules. It equals number of moles multiplied by Avogadro's constant, which is 6.02 exponential 23. As we do not know the number of moles, we only have volume. So let's first convert this volume into moles. The formula used is number of moles is equal to volume in centimeter cube, which is 462 divided by 24,000 centimeter cube. It comes equal to 0.01925 moles. Now we can convert these moles into number of molecules. 0.01925 into Avogadro's constant. The number of molecules come equal to 1.16 exponential 22. Part B. Calculate the total number of electrons transferred to produce this number of hydrogen molecules. As we know that at cathode reduction occurs. H+ ions, they move towards cathode, gain electron and form hydrogen. Now balancing this equation, we have 2 electrons, 2 with H+. So now we can see that for 1 molecule of hydrogen we need 2 moles of electrons. So to find total number of electrons with this number of molecules, we can multiply both. So number of electrons is equal to 2 multiplied by number of molecules. So total number of electrons is equal to 2.32 exponential 22. Part C. Calculate the quantity of charge in coulombs of the total number of electrons calculated in part B. Now the formula for calculating the quantity of charge is quantity of charge in coulombs it is equal to total number of electrons multiplied by the charge on 1 electron. As the total number of electrons is already calculated, we have 2.32 exponential 22 number of electrons multiplied by the charge on 1 electron, which is given in data booklet. It is 1.6 exponential minus 19 coulombs. So quantity of charge is equal to 3.71 exponential 3 coulombs. Part D. Calculate the current X passed through this experiment. For this we can use the formula charge equals current into time in seconds. Or Q is equal to I, which is current, into T, which is time in seconds. Now we can rearrange to find current X. So I will be equal to Q divided by T. Charge is already calculated in part C. We have 3.71 exponential 3 coulombs. While time is given in equation, it is 14 minutes. We can convert 14 minutes into seconds by multiplying by 60. Now it comes equal to 4.41 amperes. Part E, the standard entropies of 3 species are given in the table. We have water liquid, hydrogen gas, oxygen gas. Calculate entropy change for the reaction. We have H2O, it converts into hydrogen gas and oxygen gas. Now for entropy change, we know the formula. Entropy change equals entropy of product, total entropy of product, minus total entropy of reactants. Now in product we have 2 moles of hydrogen gas, 2 hydrogen, and 1 mole of oxygen gas, minus entropy of reactants. In reactant we have 2 moles of water. Now putting the values from this table, it will be equal to 2 multiplied by hydrogen, which is 131, plus oxygen is 205, minus 2 multiplied by water, which is 70. So the entropy change comes equal to 327. It is in joules per Kelvin per mole. Part 2, enthalpy change for the reaction is given. It is 572 kilojoules per mole. Calculate Gibbs free energy for this reaction at 298 Kelvin, which is the temperature. For Gibbs free energy, we know the formula. Delta G is equal to delta H, which is enthalpy change, minus temperature into delta S, which is entropy change. Now we can find the Gibbs free energy by putting the values. Enthalpy change is given. It is 572 kilojoules per mole. Minus temperature is also given, which is 298 Kelvin. Multiply by this value, which is change in entropy. We have already calculated that, but this was in joules per Kelvin per mole. Now we have to convert this into kilojoules, so we can divide this by 1000. This is because the value here is kilojoules, so this must also be in kilojoules. Now the Gibbs free energy comes equal to 474.6 kilojoules per mole. Part 3, predict the effect of increasing temperature on the spontaneity of this reaction. Explain your answer. For Gibbs free energy, you should always remember that it is inversely proportional to the spontaneity. So as we can see that if temperature is increased, this value will increase, T delta S will increase, and delta G will decrease. Because we are subtracting this value from 572, so therefore by increasing temperature, the Gibbs free energy decreases, so the reaction becomes more spontaneous. We can write the answer. The reaction becomes more feasible at higher temperature. And for this you can give the reason that T delta S will increase because or as T delta S becomes more positive. Or it increases. So when this value will increase, automatically delta G will decrease and the reaction will become more feasible. Question 2. Solution Y is hydrochloric acid, HCl aqueous. Solution Z is aqueous 4-chlorobutanoic acid. The formula is given. The pKa, which is ionization constant of acid, is given as 4.52. The pH of both solution is 4. Part A, we have write an expression for the ionization constant of acid for this carboxylic acid. Let's see how it ionizes. We have Cl, CH2, 3, COOH. As it is weak acid, so it will ionize within equilibrium. We have H positive ions which are formed. And we also have the negative part. Now Ka is actually the concentration of product divided by the concentration of reactants, raised to the power their respective number of moles. We can write Ka, it is product which is H plus, concentration of H plus multiplied by second product which is this one, concentration of Cl, CH2, 3, CO2 negative, divided by the concentration of reactants, which is this acid Cl, CH2, 3, CO2H, raised to the power 1, as each has 1 mole in balanced equation. Part 2. Write a mathematical expression to describe the relationship between Ka and pKa. We can convert Ka into pKa by using this formula. pKa is equal to negative log of Ka. Part 3. Calculate H plus ions in solution Y and solution Z. Now we know the formula of pH. pH is equal to negative log of H plus. So we can find H plus concentration. It will be equal to 10 raised to the power minus pH. As the value of pH is given in the question, it is 4.0. So we can write 10 exponential minus 4.0. It comes equal to 1 exponential minus 4 mole per decimeter cube. Part 4. Calculate the ratio. We have concentration of HCl dissolved in solution Y divided by concentration of acid dissolved in solution Z. In the question we can see we have H plus ion concentration, which is actually the concentration of HCl. So this is given. Concentration of HCl equals 1 exponential minus 4 mole per decimeter cube. Now we need to find the concentration of this acid. In the question they have given pKa value of acid, which is 4.52. Let's find the value of Ka from this, as pKa is equal to negative log of Ka. So we can find Ka which will be equal to 10 exponential minus pKa. Putting values, we have 10 raised to the power minus 4.52 and Ka will come equal to 3.02 exponential minus 5. From Ka expression, we know that we have Ka equals H plus concentration of ClCH2 CO2 negative divided by the concentration of acid ClCH2 whole 3 COOH. This expression was in part 1. Now we have the value for Ka, we also have the value of H plus ion concentration. As from this equation we can see that the number of moles of H plus is equal to the number of moles of this. So the concentration will be equal in both. So we can use the concentration of H plus instead of this one. This is also given. Now we can find the value of this and then we can use the value to find out the ratio. Now we can rewrite this equation as Ka equals, as both are same, so we can write H plus square divided by the concentration of acid ClCH2 3 COOH. Now we can rearrange to find this value. We have ClCH2 3 COOH concentration. It equals H plus square divided by Ka. Now we can put the values. H plus is already calculated. We have 1 exponential minus 4 square divided by the value of Ka, which is 3.02 exponential minus 5. Now we have the concentration of ClCH2 3 COOH. It is equal to 3.3 exponential minus 4. Now we can divide both these values. First one is the concentration of HCl, which is 1 exponential minus 4. Second one is the concentration of this acid, which is 3.3 exponential minus 4. So now the concentration of HCl, 1 exponential minus 4 divided by the concentration of this acid, 3.3 exponential minus 4. So it comes equal to 0.302. Part B, a buffer solution of pH 5 is produced by adding sodium propanoate to 5 grams of propanoic acid in 100 cm³ of distilled water. Calculate the mass of sodium propanoate that must be used to produce this buffer solution. The Ka of propanoic acid is given 1.35 exponential minus 5 mole per decimeter cube. Molecular mass of propanoic acid is 74, molecular mass of sodium propanoate is 96. We have two things. One is sodium propanoate, which is CH3, CH2, COONA. This is a salt. And second thing is propanoic acid, which is CH3, CH2, COOH. Both combine together to form buffer solution of pH 5. Let's first write the equation for the dissociation of propanoic acid. We have CH3, CH2, COOH. It dissociates to form CH3CH2, COO negative and H positive. We can write Ka for this equation. Ionization constant of acid is equal to the concentration of product raised to the power their number of moles. Second product is H plus divided by the concentration of reactant, which is propanoic acid CH3, CH2, COOH. In this formula we have value of Ka, which is given 1.35 exponential minus 5 mole per decimeter cube. The value of H plus ion can be calculated from this pH. we can use the formula pH is equal to negative log of H plus, or H plus will be equal to 10 raised to power minus pH. By putting the value, pH is 5, so it comes equal to 1 exponential minus 5. We can also find the concentration of this acid from the given mass. As we know, the formula concentration is equal to number of moles divided by volume in decimeter cube. So number of moles will be equal to mass in grams divided by molecular mass of propanoic acid. Molecular mass of propanoic acid is given, it is 74. So 5 grams divided by 74, it will come equal to the number of moles of propanoic acid divided by the volume in decimeter cube. As we have 100 centimeter cube, so we can convert it into decimeter cube by dividing by 1000. So concentration of propanoic acid comes equal to 0.675 mole per decimeter cube. So now we have the value for this. Let's find the value for the concentration of propanoate ions. We can rearrange this equation, CH3, CH2, COO negative. It will be equal to Ka multiplied by the concentration of acid divided by the concentration of H plus ions. Now putting values, Ka is given, it is 1.35 exponential minus 5. Concentration of acid is calculated, it is 0.675. Concentration of H plus ions is also calculated from pH, it is 1 exponential minus 5. It comes equal to 0.912 mole per decimeter cube. This is the concentration of CH3, CH2, COO negative, which is propanoate ions. Now to find the number of moles from this concentration, we can use the formula number of moles is equal to concentration into volume in decimeter cube. Concentration is 0.912 and volume is given in question, it is 100 centimeter cube or 0.1 decimeter cube. So now the number of moles is equal to 0.0912 moles. As we know that the concentration of propanoate ions from this acid is very low as the equilibrium lies to the left. So therefore the concentration of these ions is provided by sodium propanoate, which is CH3CH2 COONA. And we know that this salt is 100% soluble, so it will be converting into CH3CH2 COO negative and Na positive. Now we can assume that the number of moles of this propanoate is exactly similar to the number of moles of this sodium propanoate. So if this is the number of moles of propanoate ions, this could also be used as the number of moles of sodium propanoate. Now we can find the mass of sodium propanoate from number of moles. The formula is mass in grams equals number of moles into molecular mass. So number of moles is 0.0912. Molecular mass is given in question, it is 96 for sodium propanoate. So mass in grams of sodium propanoate comes equal to 8.756 grams. Part C, some dilute sulfuric acid is mixed with small sample of buffer solution described in part B. The final pH of the mixture is close to 1. Explain this observation. As we know from the previous part that the pH of buffer was 5. Now the pH is 1. So as pH has decreased from 5 to 1, it means the concentration of H plus ions has increased. Now from other angle we can also see that propanoic acid is CH3, CH2, COOH, and it is dissociated into propanoate ions and H positive ions. Now when sulfuric acid is added, what happens that the concentration of H plus ion increase. When concentration of H plus ion increases, the equilibrium shifts to the backward direction according to Le Chatelier principle. So therefore the concentration of propanoate ion will decrease. As we have excess of sulfuric acid, so therefore the concentration of H plus ion will keep increasing and until no more propanoate ions will be present. So now we can write that all of propanoate ions has been protonated and when they are protonated, they are converted into propanoic acid. For pH, we can also say that the concentration of H plus ion has increased as now H plus ions are in excess. So this is the reason that the pH drops down to 1. Question 3 part A, define the term electron affinity. Now electron affinity is the energy change when electron is gained. We can write that it is the energy change when 1 mole of electron are gained by 1 mole of gaseous atoms. Part B, write an equation for the process corresponding to second ionization energy of calcium. Include state symbols. Now we know that in ionization energy electrons are lost. Calcium will lose 1 electron in first ionization energy and it will form calcium plus 1 electron which is lost. And in second step calcium will lose another electron to form calcium plus 2 plus another electron which is lost. So we can write the equation for second ionization energy as follows. Calcium already in plus 1 form which is gaseous ion, it will lose another electron to form calcium plus 2 or 2 plus 1 electron. Some data relating to calcium and oxygen are listed. Select relevant data from this list to your answers to part C, part D and part E. In part C, it says oxygen exists as oxygen molecules. Use the data in this question to calculate a value for the bond energy of the oxygen-oxygen double bond. Show all your working. For oxygen, we can see we have first ionization energy, second ionization energy, first electron affinity, second electron affinity, enthalpy change for this reaction in which O-2 is formed. And this is the enthalpy change for calcium and this is the lattice energy of calcium oxide. In first electron affinity of oxygen, oxygen atom is converted into O-, -1. In second electron affinity of oxygen, oxygen will be converted into O2 negative. And we also have direct from oxygen atom to oxygen O2 negative, so we can use these three values and put them in a cycle to calculate the bond energy of oxygen-oxygen double bond. Let's draw the cycle. We have oxygen-oxygen double bond. The bond will be broken and it will form two atoms of oxygen. Now we can use the first electron affinity of oxygen, so oxygen atom will be converted into oxygen 1 negative ion, and second electron affinity oxygen 1 negative will be converted into oxygen 2 negative ion. We also have direct enthalpy change from oxygen molecule to oxygen 2 negative, which is given. Let's put the arrows. This is the bond energy, as it is the energy required to break this bond into atoms. This is the first electron affinity, as oxygen atom is converted into 1 negative ion. This is the second electron affinity, and this is the enthalpy change for oxygen molecule to oxygen negative 2 ion. Now putting the values, this is first electron affinity, and as it is -142 for single oxygen atom, now we have 2 moles, so we can multiply by 2 into -142. So it will be -284. For second electron affinity, we have +844, that is for 1 moles. So for 2 moles, we can multiply by 2. It is equal to 1688 kilojoules per mole. And for third thing, we have enthalpy change for 1 atom of oxygen into O2 negative, which is 951, as we have 2 atoms and 2 moles, so we can also multiply this value by 2. Delta H enthalpy change for this reaction is equal to 2 into 951, and this will become 1902. Now from this cycle we can see that we have started from this point, then moved till this point. So these are the 3 steps that are involved, and this is the single step. According to Hess's law, one step is equal to the several step if the product is same. So now we can use Hess's law to write an equation. 1902, which is a single step, it will be equal to the sum of these 3 steps equals bond energy plus this value plus this value. Now we can easily find the bond energy. Bond energy will be equal to 1902 plus 284 minus 1688. So by calculating, this comes equal to 498 kilojoules per mole. Question D, part 1, suggests why the first electron affinity of oxygen is negative, and then in part 2 it asks why the second electron affinity of oxygen is positive. In first electron affinity, we can see that we have neutral oxygen atoms, so when one electron is gained, what will happen, that oxygen will become unstable as it is forming -1 ion. So to gain stability, it will release energy, so therefore first electron affinity is negative. Now for second electron affinity, as we already have -1 charge, so we are adding one more electron. What will happen, that these two negative charges repel each other, so therefore we need to provide energy in order to add this electron in already negative ion. So therefore energy is required, so therefore second electron affinity is positive. So in first electron affinity we have, it is because there is attraction between nucleus and incoming electron. Neutral oxygen atom becomes unstable. And releases energy to become stable. So therefore, it is negative. For second electron affinity, we can write the reason that it is due to repulsion between negative charge on oxygen atom and incoming electron. So therefore, energy is absorbed or required to make O negative ion. Part E, calculate the enthalpy of formation of calcium oxide solid. In order to calculate the enthalpy of formation of calcium oxide, we can draw a cycle. We have calcium oxide solid, which is formed from the elements. Element is calcium and we have oxygen. So this is enthalpy of formation, delta HF. Now we also know that if we have calcium plus 2 and oxygen negative 2, these two can combine together to give lattice enthalpy for the formation of calcium oxide. Now we can see that calcium atom can be converted into calcium plus 2. Oxygen atom can be converted into oxygen negative 2. We can look into the values from given table. Enthalpy change for oxygen atom into oxygen 2 negative is 951. We can use this enthalpy change. And enthalpy change for calcium into calcium plus 2 is 1933. And lattice energy is also given for solid calcium oxide, which is negative 3517. So we can use these three values to calculate the enthalpy of formation. So now we have one value for enthalpy change for calcium plus 2 and second value for enthalpy change for oxygen negative 2 formation. According to Hess's law, this is the common product. So therefore we have two steps on this side and one step on this side, and these steps will be equal to this step. So we can write the equation: enthalpy of formation is equal to enthalpy change for formation of calcium plus 2, enthalpy change for formation of oxygen 2 negative, and lattice enthalpy. Putting values, we have enthalpy change for formation of calcium plus 2 as 1933. This value from table is 951 and this value from table is 3517. So now the enthalpy change of formation comes equal to minus 633 kilojoules per mole. Part F, the lattice energy of lithium fluoride LiF solid is negative 1022 kilojoules per mole. Identify the factor that causes the lattice energy of calcium oxide to be more exothermic than that of lithium fluoride. Explain why this factor causes the difference in lattice energies. You should always remember that it always depends on the charge density of ions. Greater the charge, greater will be the lattice energy. So we can see lattice is directly proportional to charge on ions. And second thing is the size of ion. So enthalpy change or lattice energy is inversely proportional to the size of or radius of ion. As we can see that in lithium fluoride, lithium has +1 and fluoride has -1 charge, while in calcium oxide we have +2 and -2 charges. So we can write the factor, which is the charge density. Charge density of calcium +2 and oxygen -2 is greater as compared to lithium +1 and fluoride -1. So therefore there is greater attraction between calcium and oxygen ions. Question 4. Separate samples of 0.02 moles of calcium carbonate and 0.02 moles of barium carbonate are heated until completely decomposed into metal oxide and carbon dioxide. State which of these two group 2 carbonates required the higher temperature before it begins to decompose. Explain your answer. We have calcium +2 and we have barium +2. Now as we move down, what happens that size increases. So therefore charge density will decrease. Because charge density is inversely proportional to the size of ion. On second side we have carbonate ion, which is similar in size as both have carbonates. Now we can see that if charge density is higher, what will happen that it will polarize carbonate and carbonate will break easily. If charge density is low, then it will be less polarizing the carbonate ion. So therefore what will happen that barium carbonate will require more heat as compared to calcium carbonate in order to decompose. So we can write that barium carbonate requires more heat or higher temperature. This is because barium ions have less charge density so therefore carbonate ion is less polarized. Part B. After decomposition is complete, the 0.02 mole sample of calcium oxide is taken and added to 2 decimeter cube of water. A solution is formed with no solid present. Dilute sulfuric acid is then added dropwise until a precipitate is seen. The same procedure is repeated with 0.02 mole sample of barium oxide using the same concentration solution of dilute sulfuric acid. Identify the sample to which most sulfuric acid must be added to cause a precipitate to appear. Explain your answer. You should refer to the solubilities of the precipitates and relevant energy terms in your answer. In first one we have calcium oxide. Calcium oxide is dissolved in water, so it will form aqueous calcium oxide, and then sulfuric acid is added, so a precipitate of calcium sulfate is seen. Similar is the reaction with barium oxide. Barium oxide will also form precipitate of barium sulfate. Now you should remember that for group 2 sulfates, solubility decreases down the group. It means that barium sulfate will be less soluble and calcium sulfate will be more soluble. So therefore we can say that more sulfuric acid must be added to calcium sulfate to make a precipitate as compared to barium sulfate. So we can say that calcium oxide requires more sulfuric acid to form precipitate, because calcium sulfate is more soluble as compared to barium sulfate. And the reason behind this is that the lattice enthalpy of sulfates decrease by smaller values down the group. While hydration enthalpies of sulfate decrease by larger values. As overall we can see that the solubility decreases, it means that enthalpy of hydration is dominant factor as compared to lattice enthalpy of sulfates. Part C. Calculate the mass in grams of carbon dioxide produced by decomposition of 0.020 moles of calcium carbonate. We can write the balanced equation. We have calcium carbonate, it decomposes to calcium oxide and forms carbon dioxide. As the ratio according to balanced equation is 1:1, So it means 0.02 moles of calcium carbonate will form 0.02 moles of carbon dioxide. Now converting these moles into mass, the formula is mass in grams is equal to moles into molecular mass. We have 1 carbon, which is 12. We have 2 oxygen, 32. So molecular mass is 44. Number of moles is 0.02 into 44. Mass in grams of carbon dioxide comes equal to 0.88 grams. Part 2, calculate the minimum mass in grams of propane that would on complete combustion produce the same mass of carbon dioxide calculated in C part 1. Gives you answer to 3 significant figures. Now let's write the balanced equation for propane. In propane we have 3 carbon atoms, 8 hydrogen atoms. It combusts in the presence of oxygen to form carbon dioxide and water. As we have 3 carbon atoms on the right hand side, so we can write 3 with CO2. 8 hydrogen atoms are on the right hand side, so we can write 4 with water. And now we can balance 6 plus 4, 10 oxygen by writing 5 with oxygen. Now the ratio of propane and carbon dioxide according to balanced equation is 1 mole, ratio 3 moles. Now in previous part we had 0.02 moles of carbon dioxide, so for 0.02 moles we have X moles of propane. So by cross multiplying we can find the number of moles of propane. It comes equal to 0.00667 moles. Now again using the formula of mass is equal to moles into molecular mass. For propane we have 3 carbon atoms, so 12 into 3 becomes 36, plus we have 8 hydrogen atoms, so it is equal to 44. Putting values, we have number of moles 0.00667. Molecular mass is 44 for propane. So mass in grams comes equal to 0.293 grams, and there are 3 significant figures present in this answer. Question 5, Part A, MnCl4 -2 is a complex ion. Deduce the oxidation state of manganese in MnCl4 -2. In MnCl4 we have 1 Mn, 4 Cl, and overall charge is -2. As we know that the oxidation state of chlorine is -1, as we have 4 chlorine atoms, so Mn minus 4 equals -2. So Mn will be equal to +2. So oxidation state is +2. Part 2, the MnCl4 complex does not contain any 180-degree bond angles. Draw a 3-dimensional diagram to show the shape of MnCl4 -2 complex. State one bond angle on your diagram. In MnCl4 we have 4 ligands around the central metal atom Mn. So 4 ligands can be arranged in 2 ways, either it is square planar complex or it is tetrahedral complex. In 180-degree we have square planar complex, so therefore as it does not contain any 180-degree bond angle, so it means it is tetrahedral. We can show these as this. We have manganese 1 chlorine atom, 2nd chlorine, then we have wedge structure, and then dotted. Bond angle is 109.5 as the structure is tetrahedral. Part B, a solution of cobalt 2 sulfate contains the complex ion. This is the complex ion. A solution containing cobalt H2O6 plus 2 is reacted separately with an excess each of sodium hydroxide aqueous, ammonia aqueous, and sodium chloride aqueous. Write an equation for each of these reactions. State one observation that can be made immediately after the reaction. Include the color and state of the cobalt containing product. For first one, we have COH2O6 plus 2 and excess of sodium hydroxide. Now ligand exchange will take place. As we have 6 water molecules in the complex, and we have hydroxide ions from OH negative. So 2 hydroxide ligands will replace 2 water molecules and the product will be like this. We have cobalt 4 water molecules, 2 OH, now for the charge we can see that as there was plus 2 charge on the reactant side and negative 2 charge for 2 OH negative, so negative 2 and positive 2 cancels out, so therefore now there is neutral or no charge, plus 2 water molecules that are replaced. Observation is actually the formation of blue precipitate of this complex. You should remember these equations and the color and the state. Second is the reaction with excess ammonia. We can again write the equation COH2O6, 6 water molecules, 2 positive charge. We have excess ammonia aqueous. Now ammonia can replace all water molecules, so the product will be CO6 ammonia. As we can see that the charge was plus 2 and there is no charge on ammonia as it is neutral, so the charge will remain. Plus 6 water molecules that are replaced from ammonia. The color in this case is yellow and this is soluble, so therefore it is in the form of solution. Third is the reaction with sodium chloride aqueous. Again we have COH2O6, 2 plus, and the ligand is Cl negative. So now what will happen that Cl negative can replace 6 water molecules as the size of chloride is much larger as compared to the size of these water molecules, so therefore only 4 chloride ions will fit around this cobalt. Now for 4 chloride the charge is negative 4 while the charge here was 2 plus, so now the net charge will be negative 2 plus 6 water molecules that are replaced by chlorine ligands. The observation is that this one will be blue and it is soluble, so therefore it will be blue solution. Name the type of reaction that occurs in B part 3. As we can see that chloride is replacing water, so therefore this is ligand exchange. Part C, cobalt forms the complex ion. This is the complex ion. The abbreviation EN is used for bidentate ligand, 1,2-diaminoethane. This is the structure. The complex ion shows both geometrical and optical isomerism. First is that define the term bidentate ligand. As we can see that this is 1,2-diaminoethane. On this nitrogen we have a lone pair of electrons. On this nitrogen again we have a lone pair of electrons. So therefore this ligand can interact from two places. It can donate two lone pairs of electrons and form two coordinate covalent bonds. So therefore it is called bidentate ligand. So we can write that it is a species that donates two lone pairs to form two coordinate covalent bonds or dative bonds. With the central metal atom, which is transition metal. Part 2. Draw three-dimensional diagrams for two optical isomers of CONH3 and we have two ethylene diamine and the charge is +2. Each EN ligand can be represented by using this structure. As there are 6 dative bonds, so therefore we can draw like this: 1, 2, 3, 4, then wedge, 5, 6. Again on this one it will be the same. Now among these two are ammonia. As these are the mirror images, so we can draw ammonia on this side. Then we have two ethylene diamine, so one nitrogen. Similarly, we can draw ethylene diamine on this side through this structure. Question number 6. An excess of sodium iodide is added to solution of copper 2 sulfate, iodine and white precipitate of copper 1 iodide are formed. Write an equation for the reaction that occurs. We have copper 2 sulfate, which is CuSO4, plus we have sodium iodide, which is NaI, and a precipitate of copper 1 iodide, which is CuI plus I2. Plus we have sodium and sulfate, Na2SO4. Now balancing this equation, we can see that the copper and sulfate are balanced, while iodine is 1 and we have 3 iodine on this side, so we can convert this into even number first. So if we have 2 iodine on this side and 2 this, we can have 4 iodine. Now iodine is balanced. Now we can balance sodium by writing 2 with sodium, and we can balance sulfate by writing 2 with copper sulfate. B. Part 1. Explain why copper 2 sulfate solution is colored. Now color is because of splitting of d orbitals. In copper 2 we have 9 electrons present in d orbital. As d orbitals split up into 2 orbitals, we have dxy, dyz, dxz, dx square y square, and dz square. As there are 9 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9. And because of the difference in energy between these two splitted d orbitals, what will happen that this electron requires energy to jump into the dz square, and then it will come back. And when it will come back, it will release energy in the form of color. So we can explain this that d orbital splitting occurs. Electron is promoted from low energy orbital to high energy orbital. And this happens because the frequency of light is absorbed. Now upon de-excitation, when the electron moves back, complementary color is same. Part 2 suggests why the precipitate of copper 1 iodide is white. In copper plus 1, the electronic configuration is 3d10. Now as 3d orbital is full, so therefore no electronic transition is possible, because for transition of electron we must have at least one empty space or 3d 9 electrons present in d orbital. So we can write that in copper plus 1, there is complete (3d) subshell. Therefore, no electronic transition can take place. So the color will be white. Part C. Use suitable electrode potential values from the data booklet to predict whether iodide ions can reduce copper plus 2 to copper plus under standard conditions. Explain your answer. From data booklet we can have values for reduction potential of copper plus 2 into copper plus 1. The value of E naught is plus 0.15. Similarly, the value of reduction potential of iodine into iodide is plus 0.54. Now as the electrode potential value for iodide is greater, so therefore greater positive value means the direction will be forward or there will be reduction. And if there is reduction on iodide side, then there will be oxidation on copper side. Because less positive electrode potential value means that oxidation will occur rather than reduction. So therefore we can say that iodide ions cannot reduce copper plus 2 to copper plus 1. As reduction potential of iodine is greater. Or you can say more positive. Part D, an excess of sodium iodide is added to copper 2 sulfate solution. Copper 1 iodide forms as a precipitate. After precipitation, copper plus is much lower than 1 mole per decimeter cube. Use this information and your answer to part C to explain how the relevant electrode potentials change and hence why iodide ions can reduce copper plus 2 ions. Again, writing the equation for copper plus 2. According to data booklet, the electrode potential value was 0.15 volts. Now it says that an excess of sodium iodide is added to copper 2 sulfate. Copper 1 iodide forms as a precipitate. After precipitation, copper plus 1 is much lower than 1 mole per decimeter cube. So actually this is being decreased. So if this product is decreased, then this equilibrium will move in forward direction as to form more product. So when equilibrium will move in forward direction, what will happen? That the electrode potential value will increase. Again, according to data booklet, the electrode potential value for iodide was 0.54 volts. Now as it says that iodide ions can reduce copper plus 2 ions, it means that this value will increase much more than this value. So therefore reduction will take place and this equation will move in forward direction, and oxidation will take place and this equation will move in the backward direction. So we can write that copper plus 2 to copper plus 1, which is the first equation, it becomes more positive. This is because this reaction will move in the forward direction or equilibrium shifts to the right. And the new electrode potential value will be greater than 0.54 in order to get it reduced. Now more positive means reduction, so therefore reduction will occur in this equation and automatically oxidation will occur in this one. Question 7. The structure of phenyl ethanoic acid is shown. Part A. Give the number of different peaks in the carbon 13 NMR spectrum of phenyl ethanoic acid. Let's find different carbon environments. We have this carbon atom. It consists of double bond oxygen and OH and no hydrogen atom is present. Then we have this carbon atom. It consists of 2 hydrogen atoms that are present, CH2. Then we have this carbon atom. Again, no hydrogen atom is present and this is a part of benzene molecule. Now in reference to this carbon atom or this attached group, we can see that this carbon atom has position 1 if you are moving anti-clockwise, and this carbon atom has a position of 2. If you are moving clockwise, then this carbon atom will have position 1 as compared to this carbon, and this carbon atom will have position 2. And from both sides, clockwise or anti-clockwise, we can see that this carbon atom comes at position 3. So position 1 is also called ortho position, position 2 is called meta position, position 3 is called para position. Similarly, this is ortho, this is meta, and this is para position. Now charge density on ortho, meta and para positions are different, so therefore the charge density on this carbon atom will be same as the charge density on this carbon atom, as both are on ortho positions. Similarly, the charge density on meta position carbon atom will be similar to that of this carbon atom, as it is also on meta position, while the charge density on this para carbon will be different. Now counting the number of peaks, we have 1, 2, 3, 4, 5, 6. 6 different peaks will be observed. Part B, phenyl ethanoic acid, ethanol and phenol can all behave as acids. Compare and explain the relative acidities of these 3 compounds. Let's draw the structures. In phenyl ethanoic acid, we have benzene ring and ethanoic acid is present. In ethanol, we have C2H5OH. In phenol, we have benzene ring and OH group is present. In first structure, we can see that we have lone pairs of electrons present on this oxygen atom, and the charge density on this oxygen atom can be reduced because we already have electronegative oxygen atom on the other side of carbon atom. So a double bond is formed over here, and this double bond is converted into single bond and negative charge will come on this oxygen atom. So therefore charge density on this oxygen is decreased. Due to decreased charge density, what will happen that this bond is weakened and this anion becomes more stable and H+ is easily lost. In ethanol, again we have lone pairs on oxygen atom. Now as we have alkyl group that is attached, and alkyl group is electron donating in nature. So what will happen that this alkyl group will increase electron density on this oxygen atom, and in case of increased electron density, this OH bond is strengthened, it is not weakened. So when this bond is strong, it means less number of H positive ions are formed. In third one, we have phenol. Again in phenol, we have lone pair of electrons on oxygen atom, and these lone pairs can be delocalized into the ring system. Now due to this delocalization of lone pairs of electrons, the charge density on oxygen will reduce, and therefore OH bond is weakened. Again H positive is lost. Now comparing these 3, we know that this is carboxylic acid, and carboxylic acid is more acidic as compared to phenol, and then phenol will be more acidic as compared to ethanol. So we can write that the most acidic is phenyl ethanoic acid. Then on second number we have this phenol, and on third part we have this ethanol. We can write the reasons. For phenyl ethanoic acid, we can say that negative inductive electron withdrawing effect, of this carbonyl bond, it weakens OH bond. So the anion is more stabilized. And H plus is easily lost, so therefore this is the most acidic one. Similarly, for second one, we can say that due to delocalization or oxygen lone pair is delocalized, into the ring system of this benzene, and as charge density will decrease, so therefore this bond is weakened. Again, anion is stabilized. For ethanol, we can say that electron donating alkyl group actually increases electron density on oxygen. So it strengthens OH bond. So therefore anion is destabilized as it will lose less H positive ions. Part C, phenyl ethanoic acid can be synthesized using benzene as the starting material. In the first stage of this synthesis, benzene reacts with chloromethane in the presence of an AlCl3 catalyst to form methyl benzene. Chloromethane then reacts with AlCl3 to form two ions. One of these is the carbocation, CH3 positive. Write an equation for the reaction between chloromethane and AlCl3. Chloromethane is CH3Cl. It reacts with AlCl3 to form two ions. One is given, CH3 positive. And if CH3 positive is one of the product, then second one will be negative and it will be AlCl4. Part 2, draw the mechanism of the reaction between benzene and CH3 positive. Include all relevant curly arrows, charges and structure of the intermediate. CH3 positive is electrophile, so therefore it replaces hydrogen atom from benzene ring and it is substituted in place of hydrogen atom, and the process is called electrophilic substitution reaction. Let's draw the mechanism. First is that these electrons, they attack this carbon atom. Then intermediate is formed in which the ring structure is actually disturbed. We already have hydrogen atom present on carbon and CH3 is also attached. As the ring electrons are involved in the coordinate bond between CH3 and this carbon, so therefore now ring is broken. We have partial ring structure and there will be positive charge. Now in order to stabilize this ring structure, what will happen that these electrons will come back into the ring and H plus is removed. So the product is this one, and the ring structure is restored, and hydrogen atom is actually substituted by CH3. For D, a 3-step synthesis of phenyl ethanoic acid from methylbenzene is shown. This is step 1, this is step 2, and compound Q is formed, and then this is step 3 and carboxylic acid is formed. This is step 1, and we can see that CH3 has converted into CH2Br. And in step 2, compound Q is formed, which is then converted into carboxylic acid. Part 1 state reagents and conditions for step 1. Part 2 suggests the structure of compound Q. This is CH3. Now it has converted into CH2Br. So the reagents and conditions for step 1 will be, as CH3 is alkyl group, so therefore the substitution of bromine can take place in alkyl group by the help of free radical substitution. In free radical substitution, hydrogen atom of alkane is replaced by bromine atom. So we need bromine, and we also need UV light for this reaction to occur. Suggest the structure of compound Q. Now as we can see that in step 3 we have now 2 carbon atoms present. CH2, C double bond O, OH. While in this part we only had 1 carbon atom present with benzene ring, so therefore we need to increase 1 carbon atom, and a carbon atom can be increased by using cyanide. So we can convert this CH2Br into CH2Cn. This will increase 1 carbon atom. So therefore the structure of compound Q will be benzene ring, we already had 1 carbon atom present. Now we have Cn also present. Part 3 state reagents and conditions for steps 2 and 3. As we can see that in step 2 we have formed a cyanide, and in step 3 we have converted it into carboxylic acid. So CH2Br can be converted into CH2Cn by potassium cyanide and ethanol plus heating. And then cyanide can be hydrolyzed into carboxylic acid by doing acid reflux. So we can use HCl aqueous plus heat or reflux. Part 4, draw the structure of an organic byproduct that forms in step 1. As they have given that in step 1 we had CH3 and it was converted into CH2Br. So this is the replacement of just 1 hydrogen atom. Now it is not necessary that 1 hydrogen atom can be replaced. All 3 can also be replaced, or 2 can be replaced. So we can draw either this structure. We have benzene ring, and all 3 hydrogen atom can be replaced by Br, so we can write Br3, or you can also write CHBr2. This is because free radical substitution occurs until all the hydrogen atoms are replaced. Question 8. Phenylamine, we have C6H5NH2, and ethylamine, we have C2H5NH2, can be distinguished by adding aqueous bromine. Part A, state what is seen when aqueous bromine is added to phenylamine. In phenylamine we have benzene ring and NH2 is attached. When bromine is added, what will happen that it will get attached to 2, 4 and 6 positions, and therefore bromine is decolorized. While no such reaction takes place in ethylamine, so therefore we can write that bromine is decolorized. And this product that was formed at 2, 4 and 6 position, a white precipitate will be formed. Part B suggests what is seen when aqueous bromine is added to ethylamine. As we have already discussed that there is no reaction of ethylamine with bromine. So nothing is seen or there is no change. Part C, draw the structure of organic product formed when an excess of aqueous bromine is added to phenylamine. Let's suppose this was phenylamine, we have benzene ring and NH2 was present. So when bromine was added, it will replace hydrogen atoms on the benzene ring at 2, 4 and 6 positions. So substitution will occur at 2nd position, at 4th position and at 6th position. Name the product that you have drawn in part C. Now starting from this carbon atom, as NH2 group is attached with this one, we can move clockwise. So this one will be 2, 4 and 6 position. Again we can move anti-clockwise. If this is 1, then this will be 2, this will be 4 and this will be 6. So we can name the product as 2, 4, 6. We have 3 bromine atoms, so it is tri for 3, bromo for bromine, phenyl for this benzene part, and amine for NH2. Question 9. Compound T is made by a 3-stage synthesis. Part A, in stage 1, phenyl ethanoic acid reacts with suitable reagent to form compound R. This is stage 1. This is phenyl ethanoic acid, as we have 2 carbon carboxylic acid present with the phenyl. And this is R, as we have 2 carbon acyl chloride present. Suggest a suitable reagent for stage 1. In stage 1, we have converted carboxylic acid to acid chloride. So you can use either PCl3 or PCl5 or SOCl2. So write any one of these. We can write PCl5. Part B, in stage 2, compound R reacts with ethylamine to form compound S. This is acyl chloride that were formed in stage 1. This is ethyl and we have amine NH2 group. Now it has converted into compound S, NH, and then again we have CH2 and CH3 attached with NH. Part 1, name the functional group formed in stage 2. Now we can see that C double bond O NH functional group is present, and this is called amide functional group. So the answer is amide. Number 2, identify the other product formed in stage 2. As we can see that the chlorine on the reactant has gotten replaced with NH and CH2 and CH3, or NHC2H5. So we can see that one hydrogen atom is still present with nitrogen while one hydrogen atom is lost. So this hydrogen can react with this chlorine to form HCl. So the other product formed is HCl. We can also say that this bond has broken and this thing has attached instead of chlorine. Part C, in stage 3, compound S reacts with suitable reagent to form compound T. This is stage 3. Part 1, state the formula of suitable reagent for stage 3 and name the type of reaction that occurs in stage 3. Now let's see what happens in stage 3. We have C double bond O, NH, CH2, CH3, and here we have CH2, NH, CH2, CH3. Now we can see that this group is amide functional group. And this group is amine functional group. Amide was C double bond O, NH. Amine is CH2, NH. We know that in order to convert amide into amine, we need reducing agent LiAlH4 in dry ether. And the type of reaction can be seen. We can see that oxygen is lost and hydrogen is gained, so therefore this is reduction. Part D, the relative abundance of the molecular ion peak in the mass spectrum of ethylamine is 62. Calculate the relative abundance of M+1 peak in the mass spectrum of ethylamine. To find out the relative abundance of M+1 peak, we can use the formula N is equal to 100 divided by 1.1 multiplied by abundance of M+1 peak divided by the abundance of M plus peak. Now N is the number of carbon atoms present in the molecule. We have ethylamine, which is CH3, CH2, NH2. So we have 2 carbon atoms, so N is equal to 2. 100 is actually for percentage, as abundance is given in percent, so in order to remove the percentage we use 100. 1.1 is actually the number of or the percentage of carbon 13 present in any organic compound. M+1 ion peak is what we have to find. M plus ion peak is actually the molecular ion peak for ethylamine, whose abundance is given as 62. So we have the value of N, we have 100, we have 1.1, we also have abundance of M+, so we can find out the abundance of M+1 ion peak. Rearranging this formula, now we can put the values. Abundance of M plus ion is given 62, N is 2, we have 1.1, we have 100. The relative abundance of M plus 1 comes equal to 1.36. Part 2. The mass spectrum of compound T contains several fragments. The mass to charge values of two of these fragments are 29 and 91. Draw the structures of the ions responsible for these peaks. This is the structure of compound T. We can draw it again and we can use this to write down the structural formula. We have benzene ring, NH. Now there are 6 carbon atoms and 5 hydrogen atoms in this benzene ring, C6H5. Then we have this carbon atom as CH2. Again we have CH2. Then we have NH. Then CH2 and CH3. Let's find the molecular masses of these portions. We have C6H5, 12 into 6 is 72, and then plus 5 it is 77. We have 1 carbon, 2 hydrogen, so 12 plus 2 is 14, again 14. Nitrogen is 14 and hydrogen is 1, so 15, again 14 and 15. Now we have two values, one is 91 and one is 29. 77 plus 14, it can come equal to 91. So it means that this structure of ion will be C6H5CH2, and as it is ion, so it will be positive. Second is 29, so we can add these together to form 29, 15, 15, 30, or 15 and 14 is 29. So we can write CH3CH2. Again, the charge is positive. Part E. The proton NMR spectrum of compound T shows hydrogen atoms in different environments. We have A, B, C, D, E, and F. 6 of these environments are shown on the structure using letters A, B, C, D, E, F. Use the letters to answer the questions that follow. The question relates to the proton NMR spectrum of T. Proton D does not cause splitting of the peaks for proton C or E under conditions used. So you have to remember this point. Each answer may be one or more than one of the letters A, B, C, D, E, and F. Part 1. Identify the proton or protons with a chemical shift in the range of 6 to 9. From data booklet under NMR, proton NMR values, you can see that H attached with the benzene or arene, it gives values 6.0 to 9.0. So therefore this is the hydrogen atom directly attached with the benzene ring, and the only hydrogen atom that is attached directly in the benzene ring is A. So we can write A. Part 2. Identify the proton or protons whose peak will disappear if deuterium oxide is added. Now deuterium replaces those hydrogens that are directly attached with the electronegative atoms, such as the hydrogen attached with nitrogen or the hydrogen attached with oxygen directly. These atoms can be replaced and therefore the peak will disappear because deuterium does not give peak in the proton NMR spectrum. Now in this molecule we only have this proton that is directly attached with the electronegative element nitrogen, so therefore the answer is D. Part 3. Identify the proton or protons whose peak is a triplet. Triplet means 3. And according to n plus 1 rule, where n is the neighboring protons, there must be 2 neighboring protons in order to get a triplet. Let's find out which protons will give a triplet by n plus 1 rule. Now in F we have 3 hydrogen atoms as it is CH3. In E we have 2 hydrogen atoms as it is CH2. Again in C we have 2 hydrogen atoms attached with the carbon atom, and in B we have 2 hydrogen atoms attached with the carbon atom. Now according to n+1 rule on B, we can see that the neighboring protons are 2. So 2 plus 1 will be 3. So B will give a triplet. On carbon C, we can see that there are 2 hydrogen atoms and we have 2 neighboring protons. So again 2 plus 1 equals 3. This will also give a triplet. On the neighboring protons of E, we can see we have 3 neighboring protons with E. So 3 plus 1 will give 4. So it will give a quartet. It will not give a triplet. While looking at F, we can see we have 2 neighboring protons. So 2 plus 1 will give 3 or triplet. So it is B, C and F that will give a triplet, and E will give a quartet. So we can write B, C and F. Part 4. Identify the proton or protons with the lowest chemical shift values. According to data booklet, if the protons are present in CH3 or in CH2 or in CH, they will give the lowest chemical shift values, which is from 0.9 to 1.7 ppm. If the alkyl groups are present next to carbonyl carbon, for example, we have CH3 carbonyl carbon or CH2 carbonyl carbon or CH carbonyl carbon, then the value will be between 2.2 to 3.0 ppm. Similarly, the protons next to electronegative atoms, they will also give higher value from 3.2 to 4.0. And again, the protons attached with the benzene ring or aromatic ring, they also give high value from 2.3 to 3.0. Now let's look into the structure in order to find these carbon atoms that are away from electronegative element, that are also away from aromatic ring or carbonyl carbon. Now in this structure we can see that F is attached with CH2, which is attached with nitrogen. So F is further from nitrogen, which is electronegative element, and CH2 is nearer to the electronegative element. This CH2 is also nearer to the electronegative element, and this B is nearer to the aromatic benzene ring. So therefore F is the one that will give the lowest chemical shift value. So protons attached with F will give the lowest chemical shift values. Question 10. Valine VAL and lysine LYS are amino acids. The structure of these amino acids can be found in the data booklet. The isoelectronic point of an amino acid is the pH at which it exists as a Zweiter ion. The isoelectric point of valine is 6.0. The isoelectric point of lysine is 9.7. Draw the structure of valine at pH 6.0. Now Zweiter ion is the ion that contains the regions of positive charge and negative charge. From data booklet we can draw the structure of valine. It will be like this. Now in order to form the Zweiter ion, what will happen that this part, as it is carboxylic acid or acidic part, it will donate proton, this proton is donated to NH2 because nitrogen has lone pair of electrons and this is the basic part. So what will happen that negative charge will come at this point and positive charge will come at this point. So now we can draw the structure of valine at pH 6 in which it exists as Zwitter ion. The structure will be like this. We have NH3 instead of NH2 and there is positive charge. And we have O negative instead of OH as it is the negative part. Part B, a solution of lysine is produced with pH 9.7. Dilute sulfuric acid is slowly added until the pH of the solution is 1.0. The sulfuric acid reacts with lysine to produce different organic ions that are not present in significant concentrations at pH 9.7. Draw the structures of 3 of the organic ions that form during the addition of sulfuric acid in the boxes. Draw the organic ion present at pH 1 in box C. Let's first draw the structure of lysine. From data booklet we have NH2. Then we have 4 CH2 groups attached. Again we have NH2 group. And on this side we have carboxylic acid functional group. Now at pH 9.7, lysine exists as Zwitter ion, which means that on one side we have positive charge and on second side we have negative charge. So Zwitter ion will be like this: NH2, CH24. We have one more hydrogen atom on nitrogen as it is basic part, so NH3, and the charge is positive. While on carboxylic acid part, proton is lost, so therefore it will be O negative, and this is Zwitter ion. It will be present at pH 9.7. Now we can see that dilute sulfuric acid is added, which provides H positive ions. We have 3 portions on which H positive ions can interact. One is this NH2, one is this NH3 positive, and one is this O negative. So when dilute sulfuric is added slowly, what will happen that at first the protons will be attached with this oxygen atom. So the structure will be like this: NH2, CH24, we have NH3 positive on this side, and as we are adding dilute sulfuric acid, so this O negative is attached with proton from dilute sulfuric acid, and overall just +1 charge will be present. Now in the formation of Zwitter ion, instead of this nitrogen atom, hydrogen can also move to this nitrogen atom to form NH3 positive, and this part will become negative. So as the negative part is neutralized by acid, this NH2 can be shown as positive. So this will be NH3 instead of NH2 and it is positive. This will be neutral NH2, and this part will gain proton from sulfuric acid dilute. So again the charge is +1. Remember that all 3 structures must be different. Now as in part C the pH is 1, it means that sulfuric acid is quite high in concentration, so therefore what will happen that it can provide proton to both these nitrogen atoms. So this nitrogen is already positive, and proton can also be gained by this nitrogen atom from dilute sulfuric acid at higher concentration, and this carboxylic acid has already formed. So now we have 2 positive ions. or +2 charge. Part C. Draw the structure of the dipeptide valine lysine. The peptide bond should be shown fully displayed. This is lysine. We have NH2, CH24, NH2, C double bond O, OH. And this is valine, NH2, C double bond O, OH. Now these two can react together to form peptide bond. Water will be removed and this nitrogen will make a bond with this carbon atom. Now combining these two, we can draw the structure. We have NH2, then CH24, then we have this NH2, and on this side we have carbonyl carbon, and now nitrogen is also attached. One hydrogen atom is still left on nitrogen. Then we have this carbon atom which is attached to these three and also to C double bond O, OH. As we can see that we have C double bond O and H, which is the peptide bond, and it is shown fully displayed. Thanks for watching. If this was useful, please do like, subscribe and share.